Alright, so in today's video, I want to go through Concept 4 notes, which is going to be over work and power. Remember, we are still in our energy unit, so in our very first concept, we talked about kinetic and potential energy and how you could calculate those values. In our second concept, we talked about energy transfers and all the different forms of energy that are out there. In the third concept, we talked about thermal energy and how to calculate specific heat and do thermal energy calculations involving specific heat. And now we are going to jump into work and power, and we're going to learn exactly what those mean and how to calculate work and power using a couple simple equations here. So it is not a bad idea to have out your note packet for this week. It should be included in your weekly packet from the week of March 30th. And also not a bad idea to have out your second weekly assignment for this week, which is work and power calculations. You could have that assignment out as well as the notes, because you could jot down a few notes if you had to on that assignment that might be helpful for you as you go through that one. Again, do not hesitate to email me with any questions that you might have. I'm more than willing to answer them. I could even make a video where I could answer your specific question if I had to. So feel free to shoot me an email. It should be included, my email that is, should be included on the very first page of your packet on that weekly letter. So without further ado, we'll jump into work and power. The very first question I want to ask you is, have you done any work today? And hopefully that answer is not no, because it would be very unfortunate if you just sat around all day doing nothing. I mean, we all have those days, but hopefully you're staying busy during this time. So have you done any work today? And most people are going to think of things like, well, you know, I did the dishes, or maybe I mowed the lawn, or I took out the garbage. So that could all be considered that you've done work today. And I would agree with that thought process there, that could be considered work. However, physicists think of work in different ways. So for instance, physicists define work as the transfer of energy that occurs when a force makes an object move. So physicists, when they think about it, they think really in terms of energy and objects moving, and that's kind of the key things there for work. Notice here that when we represent work, we abbreviate it with just a capital W. That's going to come in handy here in a second when we look at the formula for work, but we do represent it as a capital W. And since it is measuring the transfer of energy that occurs, that means that we are going to measure it in joules. Just like Q was the measurement of heat, and heat is just the transfer of thermal energy. That is what work really is. It's just a transfer of energy when an object moves. So we do measure it in joules like we do with all other forms of energy. And two conditions must be met. The first condition is that the object must move. That says it right there in the definition. That makes an object move. Objects must move. That is the very first condition for work to be done. If the object does not move, then we can say that no work was really done, and that might occur in your second assignment for this week. So maybe pay attention to that. You know, you might get a problem where it says the object really didn't move, and then it's going to say calculate the work done. And you should immediately realize that if the object did not move, then realistically there will be no work done in that scenario. And then secondly, the force must be applied in the direction of the movement. So basically, if you're applying a force, the object must move in that direction. So the example I have here is a person holding a stack of books, and let's say they're walking to the right. They are applying a force to these books that is being able to lift them and move them to the right. So the force is being applied in the same direction of movement, which is going to be to the right here in this example. And work can be represented by an equation. It's actually not that bad. It is going to be W, or work, equals force times distance. So we know that W is going to equal work. Again, it is measured in joules. We know that F from previous formulas, such as F equals ma. We know F equals force, and force is measured in units named after Sir Isaac Newton himself. We measure them in newtons. And distance is going to be measured in meters. So distance in meters, force in newtons, and work is going to be measured in joules. So we'll jump right into an example here. Let's say you are going to move a 75 kilogram refrigerator 35 meters. This requires a force of 90 newtons, and now you want to figure out how much work in joules was done while moving the refrigerator. So after you read through the problem, the very next thing you should do is start to define your variables. So for instance here we have 75 kilograms, and that's the mass of our refrigerator because mass is measured in kilograms. So we can write m equals 75 kilograms, and we know that we're moving at 35 meters, so we have a distance of 35 meters in this problem. And then lastly, the last number we're given is 90 newtons of force. So that is our F in this problem. So our force equals 90 newtons. And then not a bad idea to write what you're looking for, and what you are looking for in this problem is going to be the work done while moving the refrigerator. That's why we write a little question mark next to it, because it helps us figure out what we need to determine for our final answer. And then not a bad idea, even though it's written up here, work equals force times distance, it's not a bad idea to get into the habit of writing out the formula that you are going to use for each specific problem. So work equals force times distance again, and then all we have to do here is start to plug in. We're solving for work. We know we have a force of 90. We know we have a distance of 35 meters, so we can just plug it directly into the formula. So work equals 90 multiplied by 35, and we should get that work is going to be 3,150 joules. And notice here that when we write our final answer, there is something that we did not use. We did not use the 75 kilograms. That was kind of an extra added variable here that we really didn't need for this problem. So that's why it's in good habit here to kind of write out everything, because sometimes I might give you a little bit of extra information that you don't need, and you're going to have to be able to pick through the information in the problem and figure out what you need to solve the problem at hand. So in this case, 75 kilogram refrigerator, you don't need to know that information. But in a future problem, it is quite possible that you're going to need that information to figure out another aspect of the problem. You might need to figure out the force, so it might be important to know what the refrigerator's mass is. So in this problem, not that big of a deal, but just pay attention to that in the future. And remember, no naked numbers, so we have joules there for our work. Here are the practice problems for this note, or these notes. Feel free to try them out if you would like, but you do not have to. The solutions are in your notes, but you'll see them here very quickly. And then we are going to jump right into power. And there is a difference between work and power that I will highlight a little bit later, but all you really need to know is that work is the transfer of energy that occurs when an object moves, and power is really just how fast, or the rate at which work is done. So power is the amount of work done in a certain time, or just really the rate at which work is done. For instance, you have distance, which could be thought of just like work in this example. Distance represents a certain value, but if you want to figure out speed, which is just the rate of distance, you would do distance divided by time. If you want to find power, which is just the rate of work, you would do work divided by time. And that's really the only thing you have to do here. And it is represented by this equation where P equals power, and that's going to be W divided by T. It's going to be equal to W divided by T. We know that P is power. It is going to be measured in kind of a new unit here. And that unit is going to be joules per second, or joules divided by seconds, because we just said that work is measured in joules because it's a measure of energy, and time is going to be measured in seconds for this problem. So you basically can say that power is joules divided by seconds. Or there is another unit that you might be familiar with. It occurs a lot on light bulb packaging. You definitely see this on light bulbs, and it is watts. And watts is just represented by a W as well. So that can get a little confusing. I would highly recommend that you pay attention to that and don't let that trip you up later. That watts can also be represented by a W. So if you write a number for your final solution and you're looking for power, you can just write a W for watts, but make sure that you're not getting confused later. If I give you P equals W divided by T, you might be asking yourself, well, I don't have watts yet, so how can I figure out power? Just remember that the W in this formula is going to be work, not watts. I know that's a little confusing right there, but just make sure you pay attention to that. And then W again is going to be work, and it is measured in joules. And then finally, our last variable here, time, just to reiterate, it is measured in seconds. Alright, and you've probably heard of watts again when dealing with light bulbs. You might have gone to Home Depot or Lowe's or Walmart, wherever you pick up light bulbs, and you've gone to the section and you basically start looking at all these light bulbs, and you might be asking yourself, well, which light bulb do I get? Do I get the 60 watt light bulb or the 40 watt light bulb? Well, now you know that watts are really just a measure of power. So it kind of makes sense that the higher the number, basically the higher the wattage, you're pulling more power from that light bulb. So for instance, we have a standard incandescent light bulb. These are just the ones with the filament inside of it, and they tend to burn out rather quickly. And we have a 60 watt light bulb here. So that basically means that this light bulb, if you look at the rest on this list, is going to pull the most power. So that's a way of thinking of it when you're shopping for light bulbs and you're thinking of watts, is that you have a 60 watt light bulb here and it's going to be really pulling the most power. And down here, lumens, you might not have ever heard of this, but lumens is actually just a measure of how bright something is. So the higher this number here, the brighter the object, or the light bulb in this case, is going to be. So that is very important when considering wattage here, because if you look here, the lower this number gets, the better, because that necessarily means that you're going to save more money. Generally, it means you're going to save more money in terms of power consumption. Now, the bulbs themselves might be a little bit more expensive, so that kind of plays into a factor as well. But the lower this number, generally the better in terms of energy consumption. And it's also good to note the brightness, because you don't want to get a really energy efficient bulb that's really dim, because that's not going to help you out that much. But if you notice, the most energy efficient bulbs down here, which are going to be LEDs, they produce about the same amount of light as a regular incandescent bulb for significantly less power used. So that's just an interesting thing to look at, because you can save a little bit of money that way, and that's just another thing to think of, and it kind of relates to what we're talking about, which is power. And remember, power is measured in watts, and usually the lower the wattage, that is going to result in energy efficiency, and which saves a little bit of money down the line when your parents get the electric bill for the month. And then I want to jump into an example here, and this is going to be our power example. So for this problem, we'll read through it here, and we'll see that it took 150 seconds to move a refrigerator. You did 3,150 joules of work in the process, and we want to figure out how much power was required to move the refrigerator. So this is just like our example number 1. We actually found the work in example number 1, so this is the same process of us moving the refrigerator. Now we want to figure out how much power was required to move the refrigerator. So very first thing we should do next is define what variables were given, and we know that it took 150 seconds. The next thing we should do is probably define what our work is, and our work is 3,150 joules in this problem. The next thing, we are looking for power, so not a bad idea to write that power equals question mark, because we don't know what it is just yet, but we're hopefully going to figure it out. And not a bad idea to also write the formula for power, which we just looked at in your notes, and that is power equals work divided by time. So P equals W divided by time. The nice part is, for this problem, we already have the work, we already have the time, so you just have to plug it into your formula, and you should get that 3,150 joules is going to be divided by 150 seconds, and we should get that our power is going to equal 21 joules per second, or 21 watts. That is up to you. I would accept either answer in terms of units. If you wanted to do joules per second or watts, that is completely acceptable. They are the same unit technically. Alright, so in this last problem, I want to highlight the difference between work and power one last time. So in this problem, we have two identical weightlifters, and they both are going to be lifting the same mass or weight here. They're going to be lifting that exactly 2 meters above their head. The only difference is that the person on the left here is going to lift the weight in 2 seconds, and the person on the right is going to be able to lift the weight in 5 seconds. So let's examine here how much work each one of these weightlifters did and how much power each one of them did. So we got to remember that work equals force times distance, and that power equals work divided by time. And we also must assume for this problem, to make it work out really nicely, that both lifters are applying a force of 100 newtons upwards. So they are going to lift these weights up with about 100 newtons of force. So that's very important to remember as we go through here, that they are both exerting the same amount of force on a weight of identical value there. And if we look at it this way, we can figure out the work that each one of them do. Because work equals force times distance, if we know they're both doing a force of 100 newtons upwards, and the distance is 2 meters, well, that's just 100 multiplied by 2, and we should get 200 joules as the work. And remember, it is the same for each one of them, the work is, because they're both lifting the weights 2 meters, and we're going to assume that they're identical, and it's both going to be the same amount of force applied here. So we're just going to assume that these work here are going to be identical. But is their power identical here? And the first thing you've got to realize is, well, there is a difference here. This person here can do it much faster than this person here. This weightlifter is able to lift his weight in 2 seconds. This person's able to lift it in 5 seconds. So that is really where power comes into play. And what we should realize is that power is work divided by time. So we just have work here. So if we have 200 divided by a time of 2 seconds, so 200 divided by 2, we should get that this weightlifter is going to have 100 watts of power that they're doing in this time. So 100 watts is the power for this weightlifter. but they are still doing the same amount of work as another weightlifter here. And then for this second example here, if it is 5 seconds here is the time it takes, well, then we take our 200, we divided it by 5, and we should get 40 watts of power here. So that's kind of the difference between work and power. Work, all that really matters is how much force was applied and what is the distance. So in this case, it's going to be identical because we have identical forces and identical distances. But power really does take into account how much time it takes. You did the same amount of work, but how quickly did you do that work? So that's why we get more power here than we do here, because this weightlifter was able to do it much more quickly. So I hope this helps you out a little bit when doing your second assignment for this week. Again, if you have any questions, shoot me an email. It is on the front of your packet, and I hope this was helpful.